Hi, this video is about the paper Extrapolated Alternating Algorithms for Approximate Canonical Polyadic Decomposition. This is the overview of the video. We first talk about the problem and the existing approaches to solve the problem. Then we move to the proposed approaches introduced in this work. There are two approaches. Then we show the numerics and finally we conclude the paper. The paper and slide are available in the links. Now, we talk about Approximate Canonical Polyadic Decomposition, or in short, aCPD. Here is the problem description. Given a tensor T and a factorization rank R, solve the non-convex minimization problem as shown. The minimization problem is to find the minimizer of the Frobenius distance between the given tensor T and all the tensor G that has rank at most R. Here are the definition of tensor rank and the definition of tensor product. This non-convex minimization problem is, in general, very difficult to solve. Many algorithms are proposed in the literature, and we focus on the type of algorithm that is alternating algorithms. There are two categories: the exact block coordinate descent, or in short, exact BCD, and the approximate BCD. In the exact BCD, subproblem on each block variable is solved optimally. For example, in ALS, by minimizing the objective function with respect to one particular block, say block J, we obtain the closed form update as a matrix product. Here, T subscript J is the mode J unfolding of the tensor T, and the B superscript J is the product of all the other blocks. In the approximate BCD, such as various gradient update algorithm, the update of a block is basically to perform a gradient step. Here, L is the Lifshitz constant of the gradient evaluated at the current point, and B is defined as above. In this paper, we introduce and compare two algorithms for solving aCPD that makes use of extrapolation of the variable sequence, the heuristic extrapolation and restart, in short HER, and inertial block proximal gradient, in short IPPG. The goal of this work is to show that when computing aCPD, the extrapolation is in fact very useful, which agree with the traditional wisdom in the literature back to the 70s. Now we look at IPPG. IPPG is an alternating proximal gradient algorithm proposed to solve a general non-convex, non-smooth block separable composite optimization problem. aCPD is a special case of this kind of problem, so we can just use IPPG to solve it. The algorithm makes use of two different extrapolation points, as shown in the yellow block. Notice that the two blocks are used to perform the gradient update. The other feature of IPPG is that it has no restart, and it has a very flexible structure. In fact, the algorithm shown here is just one particular structure of IPPG. Finally, IPPG for aCPD have subsequential convergence. Now, we look at the second algorithm, the HER accelerated ALS. HER acceleration is an in-between block acceleration. That is, you perform the following: update block 1, extrapolate block 1, update block 2, extrapolate block 2, etc. This is very different from other methods that update all the blocks and perform the extrapolation. HER also has restart, which is also different from other algorithms that makes use of restart. Here, the criterion for restart is using the F hat, which is cheap to compute. We now explain why F hat is cheap to compute. Say you are using the objective function as the restart criterion. So, after you update all the blocks from block 1 to block P, if you want to compute the Fk, you have to compute the whole expression as it is. there's no way you can reuse any already computed component for all the block. But if you use f hat as the criterion for restart, notice that after you perform the update and extrapolate for all the block, you can reuse all the already computed component to compute f hat. The computation of f hat is actually partially computed when you update a and z. Computation of f hat is very cheap, and this is in fact the key message of this algorithm. That is, this algorithm makes use of restart to safeguard any wrong extrapolation, and the restart criterion is cheap to compute. Now we look at restart mechanism. Basically, it makes use of the f hat. First, consider the case f hat decrease. In this case, we will keep the extrapolation sequence, and then we will grow the extrapolation weight beta. The way we grow it is just simply by multiplying it with a number larger than 1, which is the parameter gamma. In that case, f hat increases, we will abandon the extrapolation sequence z, and then we will drop the beta. We just divide it by a number larger than 1, which is the parameter eta. In the process of updating beta, we also have an upper bound beta bar parameter. We also update this beta bar in a similar fashion as beta. So what are the features of her? It can accelerate any BCD algorithm, not just ALS. And as we mentioned, the restart is very cheap, so there is no additional cost in doing the restart. Finally, this algorithm does not need heavy parameter tuning. And as a side note, this approach works very well also for the non-negative CPD. Now we talk about experiments. We will compare 5 algorithms. They are IPPG, her ALS, and also the original unaccelerated ALS, and 2 different accelerated ALS using different schemes. We will test this algorithm on both synthetic and real data. On real data, we perform no preprocessing other than replacing NaN value as 0. All the experiments are run 20 times and we plot the median. We first have the result on synthetic data. We add a little Gaussian noise on the data and also adjust the conditional number of the Mo123 matrices to 100 to simulate yield condition cases. In the graph, the square bracket represents the tensor size, which is i's times j's times k because this is an order-free tensor, and also the factorization rank R. The results are IPPG in red and her ALS in blue are the best algorithm among the 5 algorithms because it converges fast in both iteration and time. Also, because the data is ill-conditioned, for the unbalanced case, that means the right column, we can see that for ALS, the thick black curve, it goes down very slow for a very long time. This demonstrated that the variable for the ALS actually got stuck in a swamp. While for the other algorithms, they are all extrapolated. 3 of them escape the swamp. Finally, for the green curve, the LS-ALS, it goes down very fast in terms of iteration, but in fact, if you look at the time, it goes down very slow. This is due to the fact that line search is computationally expensive. Next, we give the result on real data. First, we have the Y data. This data has a property that the conditional number is quite large, and therefore we can see that 3 of the algorithm has a very flat curve, and only 2 of them can escape from the swamp. Now we look at Indian pine data. We have similar result. Her ALS achieved a very good convergence result, but also for IPPG and Bro ALS. Again, because the line search is expensive, so LS-ALS is slow. Finally, we look at blood data with different decomposition rank R. Again, her ALS is the best. Overall result, all the results shows that her ALS outperform all the other methods in all cases, while IPPG shows mitigated result. We now conclude the paper. We have talked about the problem of aCPD and introduced two extrapolation-based algorithms for solving aCPD, namely the IPPG and the her BCD, where in this talk we focus on her ALS. This work shows that swarm can be a serious problem when computing aCPD, and extrapolation can be a good method for escaping swarm. In fact, these phenomena are also observed in constrained CPDs such as the non-negative CPD, where her approach works even better. Finally, the theoretical convergence analysis of her remains an open problem. This is the end of the presentation.